Again, integration by parts is a technique that uses a formula that comes from the differential of a product. So remember the product rule. The derivative of the product of two functions u and v equals the u times the derivative of v plus the function v times the derivative of u. So notice if we rearrange these parts, we get the derivative of uv minus v du equals u dv. Okay? All we've done here is kind of subtracted v du from both sides and then reverse the order here. Okay? Now if we integrate both sides, we get the integral of u dv equals the integral of the derivative of uv, and remember integrals are antiderivatives, so this is just going to cancel out, minus the integral of v du. And there we see that the integral of the derivative of uv is just going to be uv. Okay? And this gives us the integration by parts formula. Now, how does this compare to substitution? In the past with substitution, we've been looking for a u substitution, u equals a part of the integrand, where the derivative of that u was also in the integrand, okay, that what we were integrating. Sometimes, and as we've seen, we haven't had that. We didn't have the derivative of u in there. So what's going to happen with integration by parts is we're going to select a u, and then everything else that's left in there that is not equal to du, if it was equal to du, then we just use substitution. But if you can't do substitution, if du is not in there, then you select a part of the integrand to be u, and everything else that's left you label as dv. So notice we have u and dv. We also need to figure out what v is, so we would take the integral of dv. We also need to figure out what du is, so we'd have to take the derivative of u. And so we're going to walk through that, but this is the basic formula for integration by parts. We substitute something in for u in the integrand. We make a substitution, u equals a part of the integrand, and everything else equals dv. So let's see how that works. Example 1. Evaluate the integral of x ex dx. Okay? So what we want to do here is pick a part of the integral, part of the integrand is u, and then the rest will be dv. Okay? And then we just plug it into the formula. So if we let if we let u equal x, then what's left is e to the x dx, and we substitute that in as dv. Okay? But again, we need to find the other two parts. So we need to find the derivative of u, which is 1 dx. The derivative of x is just 1. And we need to find v for our formula, because it's uv minus the integral of u dv. Well, the integral of e to the x dx is simply e to the x, so v equals e to the x. Now we simply substitute them into the formula. Again, we're rewriting the integral in terms of our substitutions for u, v, v du. Well, u is x, v is e to the x, so this term becomes x e to the x, minus the integral of v, which is e to the x, and du was simply 1 dx. So u is x, v is e to the x, minus the integral of v, e to the x, du, which is dx, and of course the integral of e to the x is simply e to the x. So we get x e to the x minus e to the x plus our integration constant. If you take the derivative of this, you will get right back to x e to the x. So try that, and that's one of the good things about integration is you can always check your answer by taking the derivative, which is in a lot of cases a simpler process. Okay. Sometimes tables don't work, and let's look at, or they work in a special way, and in some cases it can be helpful, and in some cases it's just, to me, it doesn't really help at all. And this is one of those cases that I don't really think it helps at all. Okay. All right. So let's look at this. So we have x natural log of, evaluate the integral of x times the natural log of x dx. Remembering lazy people rarely excel, well, we do have a logarithm, so that is what we're going to make into our u. U is going to equal the natural log of x. dv is everything that's left, which is x dx. Okay? So if we find du, the derivative of the natural log of x is 1 over x dx, and the integral of x dx is the integral of dv, the integral of x dx is x squared over 2, using the power rule, 1 over the exponent plus 1 times the new exponent plus 1. All right. So if we plug these parts in, we get uv, x squared over 2 times the natural log of x, minus the integral of v, 1/2 x squared, du, 1 over x dx. Okay? uv minus the integral of v du. Simplifying that, we get x squared over 2 times the natural log of x, minus 1/2 times the integral of x, which of course is just x squared over 4. So we get x squared over 2 times the natural log of x minus x squared over 4 plus our integration constant. Well, what happens if we plug this into the table? Do we kind of automatically have this second integral done for us in table form? Well, our u is log of x, our integral is, x dx. Well, the derivative of what we're supposed to do is differentiate this first column until we get to 0. Well, the derivative of the natural log of x is 1 over x. If we take the derivative of 1 over x, which is the same as x to the negative 1, we're going to get negative 1 over x squared, and then negative 2 over x to the cubed, etc. And so we're never going to get to 0. So technically you can use the table method even when the derivatives won't go to 0. And what happens is, wherever you stop the table, you're actually going to integrate the last row. So when we do logs, we kind of stop when the log is gone, and we integrate the last row. So here we have the x squared over 2 times the natural log of x, that's uv, minus the bottom row, but it's the integral of the bottom row, the integral of 1 over x times x squared plus 2. So if the derivative column doesn't go to 0, you have to integrate the bottom row, and it could be a plus or a minus depending upon, these still alternate. I don't have the plus and minus here, but it's plus and minus, and if this was the third row, then it would be plus minus plus the integral. Well, why do I say that that doesn't really help us? Well, notice what we've done is, this is, by plugging it into the formula, we got the same thing. X squared, log of x times x squared over 2 minus the integral of x squared over 2, 1 over x dx. So, again, it doesn't necessarily help us. We're going to look at a couple problems from the text where it kind of does help to see it, and maybe to go through a couple of things, especially if you have to repeat the process, which is what we're going to look at now. Oh, there's the plus and minus. I'm sorry, I thought I didn't have it in there. Okay. So again, when we do the table, we get the exact same thing when we set up the formula here. So sometimes the table, in a lot of cases, the table is helpful. Sometimes it's not really all that helpful, unless it's helping you remember the formula, just finding u and dv and then doing all the parts kind of it has the formula built into it. All right, let's look at another one here. Evaluate the natural log of x squared. Find substitutions for u and dv. Again, we have a log, so our u is going to be equal to the natural log of x squared, and our dv is just going to be what's left, which is only the dx. So taking the derivative, we get 2x over x squared. This is a chain rule, right? So the integral of the natural log is 1 over the argument, 1 over x squared. And then, of course, we have to take the derivative of what's inside, which the derivative of x squared is 2x. So we get 2x over x squared dx, which simplifies to 2 over x dx. Taking the integral of dx, notice this is the integral of 1 dx, and the integral of any constant is that constant times the variable x, okay, or the variable we're integrating with respect to. So we can plug this into the formula. We get uv x log of x squared minus the integral of v du, x times 2 over x dx. This is a very simple integral to solve. So we get the integral of just 2 dx, and of course that is the integral of 2 dx, just 2, is 2x. Here, if we plug this into the table, again we have the same kind of situation where it really doesn't help us because we still have to integrate that last row. So, often with logs, it's not so helpful to solve it in this way. All right. Sometimes when you're using integration by parts, you have to use this formula. You use it for the first time, and then when you get to this, this part of the formula, which is minus the integral of v du, sometimes here you have to do integration by parts all over again. So you have to find a new u and a new dv in this process. This is often where the table can help because it handles those multiple substitutions when you have to do it again and again. And so this is repeated integration by parts where you have to do a separate integration by parts for this piece of the original formula. Okay, so let's look at this equation. The integral, integrate x squared e to the 2x dx. So again, we don't have any logarithms. We do have a power function, so this is going to be our u. Lazy people rarely excel. Logarithms, power, radicals, exponentials. We do have an x squared, that's a power, so that is going to be our u. Du, of course, is dx. And the integral of e to the 2x dx is going to be 1/2 e to the 2x. Okay? We would find that by substitution. Setting the integral of e to the 2x, we'd have to have u equals 2x, then du equals 2. We don't have a 2 there, so we'd have to offset it by its reciprocal that we saw, I think, in the last section. Okay? All right. So now we're ready to set up the formula and substitute in. Oops. So we get uv 1/2 e to the 2x times x squared uv minus the integral of v 1/2 e to the 2x times du 2x, and so we get the 1/2 and the 2 cancel out, and we get the integral of x e to the 2x. Well, notice this is another formula that we can't do substitution. If we try to do substitution and set u equals 2x, then du equals just 2, and we have this extra x factor here. So we actually have to do a substitution, a second substitution, using integration by parts. So we would go through this the same way, and in the second one we'd say, okay, in this case, for this integral, u equals x. Again, we don't have any logs, but we do have power. So u equals x, and then dv equals e to the 2x dx. We find du, which is simply 1 dx. We find the integral of e to the 2x, which was what we did before, so v in this case equals the same thing. So now for this one part, we substitute in uv. So we have this first term minus this new uv minus the integral of v du. Okay, uv, which is 1/2 x e to the 2x, uv, and remember we're minusing all of this, that's why we put the minus out there, minus the integral of v du, minus the integral of v, 1/2 e to the 2x dx, v du. Okay. Well, now we can take this integral, we can solve this integral again using substitution, u equals 2x. So du equals 1/2, I'm sorry, du would equal 2. We don't have a 2 in there, so we'd offset it by another 1/2. And so we get the final answer, which is 1/2 x squared e to the 2x minus 1/2 x e to the 2x plus 1/4 e to the 2x plus c. Okay? We could simplify that by factoring out common factors, which 1/4 is a common factor. And then, of course, e to the 2x is in each of those terms as well. All right. So let's look at this problem again. We've just gone through this problem. But instead of doing it using the formula, let's use our table method. So we start at the original, u equals x squared, and dv equals e to the 2x dx. We differentiate the first column until we get to 0. The derivative of x squared is 2x. The derivative of 2x is 2. The derivative of 2 is 0. Now we integrate the second column the same number of times, and we're doing this all with the same substitution. U equals 2x, so du equals 2, and again we don't have that multiple of 2, so we have to put its reciprocal outside. The integral of e to the u is e to the u, and then times that coefficient. Well, now we have a 1/2 outside, and again we're taking the integral of e to the 2x, so again there's a 1/2 coefficient. So we have 1/2 times this, or e to the 2x over 4. We do it one more time. 1/2 times 1/4 gives us 1/8. And we have all these terms. Now remember what we do is we add and subtract all of the diagonals. And so we get x squared e to the 2x over 2 plus x e to the 2x over 2 minus e to the 2x over 4 plus c, which is the exact same answer we got before. But for me, I think sometimes this table, in cases like this where we have these wash, rinse, repeat, or repeated integration by parts, the table method often helps. And it helps a lot, I think. I don't know. It makes it simpler to me. Instead of, again, thinking, okay, wait, what is my new u? What is my new dv? And I can get confused between the old and the new and substitution. So if I use the table, this normally helps me stay a little more coherent and not make some simple mistakes. All right. Let's look at another problem. This is from your text, example 4. Evaluate the integral of e to the 2x sine x dx. Okay. Again, if we tried to, here we have an exponential and a trig function. I don't know what we could do substitution-wise. You can't make u equal sine x because du is not going to be anywhere near an exponential. So this is a perfect example another problem for integration by parts. Okay, no logs, no powers, no radicals, but we do have an exponential. We got all the way to lazy people rarely excel. So we're going to set u equals e to the 2x, and then our dv is everything left, which is sine x dx. Okay. Well, notice if we start differentiating e to the 2x, we get 2e to the 2x, then we get 4e to the 2x. We're never going to get to 0 again. Okay, so sometimes this tells us, hey, let's not do that. Let's use the formula. Okay, but sometimes the table can help us simplify, and you can always use the formula. The table's just like a tool that works sometimes and not work sometimes. Remember, when we differentiate and use the table and we can't get to 0, we can stop at any row, but we have to integrate the bottom row. So we'd have plus, minus, plus the integral of the bottom row in this case. Okay, so why did I stop there? Well, this is going to go on, but notice what happens when we write this out. We get the first diagonal, negative e to the 2x cosine x, minus the second diagonal, but minus a negative sign. Minus a minus is plus, so we get plus 2e to the 2x sine x, and then plus the integral, but it's the integral of a negative number, so we can pull that out. We can pull the 4 out. So we get minus 4 times the integral of e to the 2x sine x. Well, notice this integral is the integral that we had originally. And that's why I stopped there, because I could see that when I integrate this, I'm going to have the original integral. Now remember, what we have here under this number 2 is equal to this integral. It's the integral of e to the 2x sine x dx equals this. So if we write that here, notice what we can do is we can now solve for this algebraically. By using integration by parts, we got another form of that exact same integral, e to the 2x sine x, e to the 2x sine x. So what I'm going to do is put all of these terms on the same side. I have a multiple of 4 of them here, negative 4. I'm going to move these all to the left side of the equal sign and solve algebraically. So the first thing I'm going to do is add 4 integral e to the 2x sine x to both sides. Well, 4 kittens plus 1 more kitten gives me 5 of them, so I have 5 of those integrals. Well, remember, we're trying to figure out what this equals, so all I have to do now is divide the right side by 5, or multiply by 1/5 to get rid of this coefficient, and I now have the answer on the right side. So if I multiply the right side by 1/5, here I've done some cleanup, so I've done a couple of things in the same step. I also saw there was a common factor of e to the 2x. So I factored those out. Again, I multiplied both sides by 1/5. I factored out the e to the 2x, and so I get 1/5 e to the 2x, 2 sine x minus cosine x, and of course we add our integration constant. Okay? So in this case, your book does this a little bit differently. It actually walks through the steps, and that's fine too. You can see, okay, well, what is this integral? Do your substitution, and you would, keep moving down until you saw it, and then hopefully you'd recognize, hey, that's the same integral we started with. So now, since I have it on both sides, I can solve for it algebraically by adding or subtracting depending upon what the coefficient was. Okay, if you want to see this done without the table, go to your textbook and look at example 4 in section 8.4. Okay. So one of the last concepts we want to look at is, how do we use integration by parts when we have a definite integral? And remember, a definite integral is just an integral with values on the integration symbol. Specifically, the values we're going from it's the interval we're integrating over from x equals a to x equals b. Don't get confused by this formula. This is just the same formula. It's a little bit written further out in notation, u of x, v of x, but it's the same formula, uv minus the integral of v du, written as u prime. So notice here what we're going to do is we're going to apply the limit to both the product of uv and the integral within the integral, so to speak. Okay, that's all this is saying. So don't get confused. It's actually quite intuitive and probably what you would think to do. If I'm going to evaluate it from a to b, I'm going to plug in the values of a and b and subtract them. All right. So let's do an example. This is example 5 from your text and see how this works out. Again, lazy people rarely excel. Lazy, we do have a logarithm. So our u is going to equal the natural log of x. dx is whatever's left, and the only thing left is dx. And we could build our table, but when we do this, the table doesn't help us at all because we only have 2 rows, and the bottom row we have to integrate. So it would have been just as easy to figure out, okay, what is the derivative of u? 1 over x. What is the integral of 1 dx? It's simply x. And then plug these values directly into the formula. u v minus the integral of v du. Okay, you can see all those parts up there. So in this case, to me, the table doesn't really help. The table helps sometimes when I'm struggling with solving the problem, or if I have repeated, definitely helps when I have repeated integration by parts. Okay, wash, rinse, repeat that we did. So if I simplify the integral here, x times 1 over x is just 1, and the integral of 1 is simply x. And so I get the integral of log of x dx is simply equal to x log x minus x plus c. Now remember, I want to integrate this from values over the interval from x equals 1 to x equals 2. So I'm just going to apply that entire limit to my entire formula here, x log x minus x. Remember, when we do definite integrals, we do no longer have a constant of integration. It's figured out in the formula. So I plug in the upper limit 2, or b, from the general formula, minus the lower limit, plugging in 1 and solving, and I get a value here. This is directly from your text, okay? I'm not going to walk through that. You can see that. And this actually gives us a new formula to add to our integration formula. So you want to plug this into your notes. So the integral of the natural log of x equals x log x minus x plus c. Again, add this to your note formula for your integration formulas. So our last example in this section is going to be applying integration by parts to a solid of revolution, as we saw before. Let R be the region bounded by y equals the natural log of x, the x-axis, and the line x equals e, as you can see in the diagram to the right. Find the volume of the solid that is generated when the region R is revolved around the x-axis. Well, we can see that when we're revolving it around the x-axis, we're going to have a circular figure or a disk. And remember, so each of those disks, the area is going to be the area of a circle, or pi r squared. And in this case, the radius is going to be the function, natural log of x. So we can figure out our formula using the disk method. The volume equals the integral from 1 to e of pi times the radius, which is the natural log of x, squared dx. So now we just, use our methodology that we know for integration by parts. What is our u? Lazy people rarely excel. In this case, we have the natural log of x. So our u is the natural log of x squared. And then, of course, our dv is what is left, and that's really only dx. Now, you might be saying, well, what about the pi? Well, remember, pi is a constant, so we can pull that outside and just plug it outside of the entire formula so that it doesn't get mixed up in our calculations and sometimes can confuse things or create some mistakes inside. I'm not going to use the table method again because we're not going to go to 0. And so I'm just going to find du, which is using the chain rule, 2 times the natural log of x over x. And the integral of 1 dx is simply x. So now I'm just going to plug this into my formula here. Now I have to remember that I've pulled pi out in front here, so I need to multiply the entire thing by pi. So I get pi times uv. U is ln x squared, v is x, minus the integral of v du. Okay, v is x, du is 2 log of x over x, du. Okay. If I now go ahead and simplify the integral, etc., notice that I just get 2 times the natural log of x in here. And then, of course, I'm going to evaluate both of those parts, the product and the integral, from 1 to e. Okay, so I have uv x log x squared minus 2 times the integral of the natural log of x, as those x's canceled out, dx, etc. And we can move through and solve, as you can see. This is directly from your text. And again, I've kind of copied these in here where they show some related exercises. I've done that very intentionally. I think you should go ahead and try the exercises in the book, at least try one of them to prepare for the text and also just to master this topic area.